So, today we will be starting with duct keels. Wing tanks, we have talked about it yesterday. Duct keel. We have been talking about the keel plate, bottom shell plate, right? There the central plate at the bottom shell was the keel plate. Now, here is some concept called duct keel. As you can see in this picture, in this figure, this particular assembly is the duct keel. That means this one, the one which is encircled, that particular construction is referred to as duct keel construction. It's nothing but it's part of the double bottom, right? We are separating it out. Like we have talked about double bottom, that you can see already. This part of the thing is familiar. There we have the plate floor, the bottom, inner bottom longitudinals, stiffeners, and here instead of a central line girder, I have two side girders, right? Previously we have seen that one central line girder and a keel plate below. So, here what has been done is the central line girder as if has been replaced by two side girders, right? Two side girders, and well, rest everything is remaining same. Only one half of the thing we have shown, the same thing is on the other side also. So, this arrangement of two adjacent side girders near the central line, that is referred to as duct keel. Duct keel arrangement is nothing but it is forming a duct, right? This space, if you can, as you can see, is forming a clean duct, and this is running all along the length of the ship, isn't it? It will be to some extent in this fashion, as we can, as I have tried to show it here. These are the two side girders running along the length of the vessel. It's only in one block we are showing. So, here it's a, these two are watertight side girders. So, this space becomes a protected closed duct. What is the great significance or great use of this arrangement? Well, one is definitely it provides a much better support for the ship structure. We had been talking about putting the ship on keel blocks, right? There we have talked about the central line girder is there, you have the keel plate, below that you have the central line row of keel blocks, right? Here the keel block, if I put it, so it gets a even better support, like say here. So, the vessel gets a much better support, isn't it? Because it is now the whole load is being shared by two girders instead of one by two girders. So, that is one advantage, right? Second advantage, obviously, instead of one girder, I have two of them. Instead of one central line girder, I have two of them. So, obviously, it provides for higher longitudinal strength. Okay. And thirdly, which becomes very effective, that is this particular duct can be used for so called laying the pipes or various kinds of ducts, whatever, cables, right? Because all along the length you will have all kinds of pipelines will be running, electrical cables will be running. So, in otherwise had there been no duct keel, they would have had run through this double bottom space somewhere, right. So, in some places they would have been totally, I mean, if the double bottom, that particular space is being used for say ballasting, so would have been submerged in water all the time whenever it is ballasted condition. Whenever it is empty, okay, fine. But here what happens, they get a very neat and clean environment. So, that way the maintenance of these pipelines or cables becomes easier, and the possible corrosion of the pipeline is also less, isn't it? Otherwise, it would have had to pass through spaces where you are carrying fuel oil or carrying fresh water or carrying ballast water, something like that, right? So, that way this duct, this space, not only it helps in providing better strength, but also provides a good space for passage of these pipes, cables, etc. If there is anything else needed, some duct, some ventilation duct or ballast pipe, drainage pipe, various kinds of piping systems are there, right. So, that space can be used. Now, as far as the structural details of that is concerned, as you can see in this part, the rest part of the dowel bottom, it is longitudinally stiffened, right. But here we have drawn transverse stiffeners. This is a transverse frame in this, and at the bottom also is a transverse stiffener. Instead of having any longitudinal, because we are not getting any longitudinal, why? Because the spacing is the frame spacing. This is one frame space. Generally, the side girders will be placed one frame space port starboard. That means that size of the duct will be twice the frame spacing, right. If it is twice the frame spacing, then either you provide a central line, sort of central line, I mean at the center line some bottom longitudinal and inner bottom longitudinal here, or provide transverse stiffening member. Here transverse stiffening member, that is a preferred stiffening arrangement, because in that case what happens, over this you can lay the pipelines, you can lay the cables. What happens is, we have talked about that longitudinal framing system is better to adopt, isn't it, because of its superiority in terms of buckling strength. Now, here what we are doing, we are little bit deviating from that. I am just drawing this part, only the, well, say the duct keel part, right. So, well, the stiffeners are like this. This is my frame spacing, they are equal spaced. Well, so here the unsupported span of the tank top plating or the inner bottom plating, as well as that of the bottom shell plating, is becoming twice the frame space, because here we have the two girders spaced one frame space apart, right. So, naturally you will have to have a strengthening member like this, because no point giving another central line girder here, then the whole purpose is lost, right. So, if I provide like this, it is also feasible solution, one can provide, right. Then what happens, I have to keep the, and I am saying that this space now is becoming available to me. I can as well keep it empty, I can as well use it for ballasting, I can as well use it for fresh water, anything. But for that, all these spaces are already there. So, what happens, this space is gainfully utilized for passage of pipes, cables, ducts, right, that becomes convenient. So, if that is so, then I will have to lay the pipes, for example. How do I lay it? Because you cannot just like that keep the pipe just on the floor, you have to tie it, clamp it, right. So, then what happens, you have to keep the pipes on the shell, which is also preferably not a very good idea, because how do I then clamp it? Means, well, to the shell, then it has to be clamped to the shell. So, I will be unnecessarily doing some welding here, which is may not be a good idea. Why? Because in the time, all these pipes sometime or other will need some maintenance. You have to open it, replace it, repair it. Then every time you do that, this welding has to be cut, re-welding, and that is not a very healthy thing to do on the shell plate, because by way of doing welding, you may impart some flaw there, which eventually can cause some more further damage to the structure. So, instead of that, it will be better if you have some platform, some support over which you lay the pipes like this. So, in that case, what you do, instead of having longitudinal stiffener here, we have transverse stiffener. Transverse stiffener. These pipes are no more there then, right. So, this is, that means at every frame space you put transverses. Like in this plane you have the floor, similarly the transverse stiffeners, but they will go for every frame space, right, like this. So, well, this frame is referred to as bottom frame, of the duct keel, and this is referred to as the reverse frame of the duct keel. You know, all members, they have some name. So, that is what is the name. This is the bottom frame of the duct keel, that is the reverse frame of the duct keel. Now, so that is how it provides necessary strengthening to the bottom shell as well as to the inner bottom plating, and also provides now sufficient space you have, as well as proper means of keeping your, laying your pipelines and cables and all other things, utility services, whatever lines are to be taken, right. So it can be laid there.
The purpose of this transverse plate is only for laying these pipes.
Main purpose is for stiffening this unsupported span, right. Main purpose is that, and while doing that, I get simultaneously as a byproduct a good surface or a good support. It does not give a surface as such, because you have the frames at intervals, but I have one horizontal plane where I get a good support to put these pipes, cables, etc. Main purpose is providing stiffening, to provide strength, to give the required section modulus, because if the stiffeners are not there, under load this will deflect, isn't it, because it can sustain an unsupported span of only the frame space.
So, then it will be better to go for a longitudinal frame.
Longitudinal, it's not a question of better or worse here, because if I provide longitudinal frame, well, it is supported. It's a transverse frame, it is actually better supported, because your, then what happens, the entire plate is supported here, right, and I am providing at every frame space. Only thing, to provide the proper load path, you have to put the brackets like this, right, with this side girder. Now it is bracketed. So, brackets are provided.
So, sir, no need for that longitudinal.
There is no more need for longitudinal. This longitudinal is not there. The construction is like this, right? Or a cleaner version, let me draw, I will show you. So, what is happening is, you have this my bottom shell plate and the inner bottom plate, right. Then you have one side girder, the other side girder, right, and then you have your, well, let us draw by different color, it will be visible better. So, this is reverse frame. This significance of this dotted line, what does it mean? This dotted line I drew, what does this signify?
Angle section.
Hmm?
So that is an angle section.
No, that there is a flange. Okay, that is a very particular answer. Angles. It can be also a bulb section, right? But not T section. Had it been T section, this line would have been continuous. It's a flanged stiffener. That flange can be a flat bar, right? That of an angle section, or can be a bulb section. If it is a bulb section, that is also a kind of a flange. That is also shown by dotted line, dotted or firm line. Dotted line means it's on the other side of this plane, right? Why I have shown in dotted? Just to show the bracket in full lines. Otherwise, that means the bracket is on this plane. Had this dotted line of this stiffener would have been, I would have drawn a firm line. The bracket is on the other side. There is a simple thing, but these are important because you see where you will put this. Okay, let us first draw the bracket, then we will come back to this. And the bracket is something like this. So, this is welded, right, and obviously the other leg of the bracket is welded to the girders. Okay. So, this arrangement is repeated at every frame space along the length of the vessel, right. This arrangement is repeated at every frame space, right. So, what happens? This is very well stiffened, right. I mean to take any load whatever is coming on the deck, on the tank top, as well as when it is being put on the keel blocks, because what happens is the keel blocks, as we have told you, that they are not, I mean they are only at interval, right. Obviously it is not a continuous support. This is my ground level, and you have the keel blocks like this. A block of woods, stack of woods, particular dimension over which it sits, right. There can be three such rows of blocks over which the vessel sits, because how you build the vessel, when those we have talked about units and blocks, right. Those blocks have to be joined together. How do you do that? So, those blocks are brought and placed over such blocks, keel blocks. They are aligned properly and welded. Entire hull is welded, and then all the necessary structural connections internally are made. All the pipe connections, cable connections, all continuity are done. So, once that is completed for the entire length, then this whole thing has to be lifted and put in water. Is it really lifted and put in water? It is either slid down, right, or floated up, one of these two. Okay, little bit we are deviating from our thing, but still maybe that is worthwhile to know. So, there are two ways of doing it. Say so it can be something like this. When we are talking about kill blocks, that becomes more relevant in this case. This is the case, this is a cross section. What we have drawn is that of a, what is it? What do you think it is? I have tried to draw. Is it not telling you anything? This is the ground level. What is this? You are not say a ship is built, right? It is delivered, it's serving purpose, then say after 5 years you have to bring it back and do some underwater repair, right? I mean the underwater part of the hull, the painting has got spoiled, or some say some small damages have taken place, or whatever. Even if nothing has happened, there is a mandatory requirement that you will have to make it dry and do thorough inspection, and whatever flaws you find, you will have to do necessary repair. How do you do that? You have to bring it to the shore, isn't it? You have to lift it up in the shore. How do you lift it? Is it physically possible? Then what do you do? Dry dock. This is a section of a dry dock, right? This is what is a so-called a dry dock.
Water is removed from it.
Yeah. So what happens? The dry dock, it extends to the waterfront. There are gates, vertical gates. So this is the dock. You have the vertical gates. So if you open the gate, right, water will come in. Right. You close the gate, pump out the water, it becomes dry. That is how. So anyway, for taking in water, we do not open the gate, we rather pump in water and then open, because suddenly you open, everything will get, you cannot do that, and neither you can open it, the amount of force it will be. In any case, so there is a dry dock, right. So in this dry dock, so one of the different thing about, I mean, when we had been talking about the various characteristics of shipbuilding industry, this is another important phenomena in this particular industry, that is that for any other industrial product, right, delivery to the customer is not a very big issue. Delivery, physical delivery to the customer. I mean, when we talk about the so-called industrial product of so-called nature of what can we refer to as commercial nature or consumer nature, not commercial, consumer nature, then it is even the customer himself take care of the delivery. Means when you buy a television, generally you go to the shop, bring back the television. So mechanism of delivery is, he puts it in, the seller puts it in a packet which is comfortable to handle. That means one can lift it, put it in car, whatever, right. When you take a delivery of a car, automobile car, so you just drive it out from the showroom. When you take delivery of a aircraft, also same thing, you just drive it out from the hangar. But when you take delivery of a ship, you cannot drive it out. You cannot lift it and put it in your car or any such thing. It has to be first made waterborne. First you'll have to put it in water, then only you can drive it out. An aircraft, will remain on ground. You can, of its own power, you can drive it out and fly off if you have an airport nearby, of course. So, this is very peculiar. I mean, this particular product, you will have to first put it in water, and that putting in water itself an exercise, because the size is such that you cannot sort of lift it and put it in water. So, it has to go of its own weight, using its own weight, slide it down. That sliding down, so this process of putting these vessels in water is termed as launching. Launching, right? So, it can be launching through a slipway, launching means putting it in water, because the trouble is you cannot go on constructing it while afloat. You can, there is nothing that you cannot, you can, but it makes your life much more difficult. Instead, if you have it static, because on water what will happen, it will keep moving, right, and not everything you will be able to do. Say the hull work, you will have to do on shore. Doing it in water also it is possible, but that will be a much more difficult task, right. So, you put it in, it has to be on shore. So, once the whole thing is built, it becomes so huge. So, putting it in water itself becomes an issue, and that one way would be through a slipway. You slide it down. It sounds very interesting, slide it down. I mean, sounds like this. Of course, I am drawing it in a very exaggerated fashion. The angle, this angle is never this much. This is referred to as declivity. So, this is my water level, right. So, what happens? It slides down. When it is sliding down, what is the guarantee that it will not go and plunge in water? The way I have drawn, isn't it appearing that when it is sliding down, it goes like this? So, thing is, it has to be so designed, the whole process of launching, that when it goes and it floats up, almost the movement of this pen, it would be like this. It will go in water, right. At certain point, it will start turning like this and become a float. If that does not happen, then what happens? It goes and opposite, straight goes. So, because your this will be the built up space. So, if this happens, that means it is going in water, and then it should float up. What does that mean? That means it should go on getting buoyancy, develop sufficient buoyancy such that a moment will start working and putting it up. So, this moment and going down moment, which is called tipping moment, right. Difference between these two, the putting up moment should be positive, I mean higher. So, that means it matters where the CG is, isn't it? Otherwise, what will happen? It will go and it will just plunge in water like this. So, that is what is called anti-tipping moment. Anyway, so you can see this itself, the whole process is tedious. Not only that, it will go float up and will not remain steady, it will keep drifting. And you imagine your river width, I mean where you are launching, suppose you are launching on a river width is whatever is the width, not sufficient, say 800 meter. So, it goes in water and it will keep drifting and go and hit the other side. You can't stop it. Had it been a car, you could have jammed the brakes. Here what you do?
Run the engine in operation.
You cannot run the engine because when you put it in water, still the engines are not fully installed, because ships are put in water from slipway in a semi-complete condition. Semi-complete means all the steel work has been done, but many of the fitting out works will be done elsewhere. Why? Because the slipway is an expensive thing. Because like a house you built, you erect the walls very fast, but then a substantial time goes fitting for the plumbing, electricity, all that. Same thing in ships. The erection of the hull, that means the hull work, steel work is very fast, but then putting the machineries, laying the pipelines, the cables, means fitting out work, all kinds of auxiliary machines, everything. It takes much longer period. So you cannot keep the slipway busy engaged on that, because that can be done while the vessel is afloat. In the afloat condition also that is possible to do, because you will be working on board the vessel, inside the vessel. So no problem if there is outside water or if the vessel is floating and making some movements, no problem. So that is why it is launched, right? When it is launched, obviously propeller, shaft, everything is fitted on that condition. So you do not have power, so you have no mechanism to brake, so then it may go and hit. Then what is the solution? So you will have to have arrangements for braking. There are ways of, you have chains connected which is clamped on the shore. Now if you really connect it in such a fashion that the vessel goes, and you can imagine the momentum, right? So either it will break the chain or it will tear off the plate where it is connected. So purpose is not served. So that is what is very interestingly done. These connections are such that slowly when it will go, it will float in the water, gradually the tension is coming on this chain, right? One after another will start failing in a sequential fashion. So that will absorb that momentum. In such a fashion it will fail that it will not cause harm to the hull, but only to that connection where it is connected, that will give way, right? And one after another. That is very interesting, it is done. Another solution is, but still there is a risk. If you do it very wrongly, your hull gets damaged, or you are too careful to protect the hull, then the braking distance becomes ineffective, means you go and hit the other side. What is the other solution? Side launch it. You know, instead of launching it, end launching, this is called end launching. It launches and it goes and hits. I launch it sidewise. So then, because then what happens? The breadth is much less than the length, minimum 4 to 5 times less, minimum. It can be 6 to 7 times less. So if I have a width, so I have ample space to, it will automatically stop. And not only that, when it goes along the length, so its resistance is minimum. So whatever momentum it is getting, with that momentum it will go on flying. But if I launch it sidewise, huge resistance, huge. So it will just launch and stop of its own, it will not go. But the problem of tipping is much more, right? So that's a very tedious job. So all these operations are very clumsy and very difficult, I mean tedious. I won't say difficult, tedious. Best is you build it in a dry dock. So what you do in the dry dock, the dock is dry, means the gate is closed. You have the rows of keel blocks laid, and depending on your handling capacity, either you start installing the sub assemblies here. Generally minimum thing installed is the units, means that say that with the double bottom you start and then bring the side shell erect, or if you have more handling capacity, this entire block is fabricated in the shop floor. From there it is transported here, hanging in a crane you can do. I mean, well, from the shop floor you will not bring it hanging, you will bring in transporters. There are specific heavy duty transporters which can carry such loads. So, you will bring it, and from there with a crane you put it on the kill blocks, right. So, there the function of the kill blocks come mainly, right. And when everything is complete, and here the advantage is you complete everything and then start taking in water inside, release it. So, it will float up automatically and goes out, right. So, that is how well I mean, when it is on sleepaway, this case of kill blocks are not there. There is a different kind of support, but when for construction or for repair or for maintenance, for dry inspection, you have to put it in a dry dock, right. This is a dry dock. So, where it will sit over these kill blocks, right, and the load on this comes. So, you can see the entire load of the vessel will be supported at only certain points, sort of 3 rows of blocks, I mean 3 columns of blocks and certain number of rows, there will be some sufficient gap between them. So, the entire weight of the vessel are supported in these points. So, naturally the structure has to be there very strong. How these kill blocks will be laid, that also will depend on, I mean, if we see inside what is the construction, you will have to have where the kill blocks are to be spaced, you will have to have some heavy stiffening members there. You cannot keep the block somewhere here, that place will get dented, isn't it? So, that is also is one aspect of the stiffening members, that means to support the load. So, that is how is what we see is the duct keels, the function here, and here as we see that the connections are with brackets. So, one can have, this is the most simplest way of doing it, that means you have 4 separate brackets. So, the alignment problem is not there at all, or it can be converted into one piece like this, just one piece of, also it can be converted like that. That means here you have the bottom shell plate one side, this is the reverse frame, you have the bottom frame, and you provide a bracket of this shape. That is also possible. Then what happens, in addition to its making, the function of brackets are to provide for the end connection, proper end connection, proper I mean to provide for adequate load bearing area, right. Because if I have the, instead of providing the bracket, if I would have extended the frame and welded only on there, that means say you have the side girder and I just extend it right up to the end, this corner I cut it off, there is needs to be cut off because of the fillet welding there. So, I get only this much of welding area, the welding area is much less, isn't it? By providing a bracket, I am increasing the welding area so much. That means the support, the load support is increasing. Okay. So, if I do it this way, as far as the reverse frame and the bottom frame is concerned, they are perfectly fine. But what about the stiffening of these girders? Because they will be there at every frame space. So, either I have to provide a stiffener here additional, or I make it as a continuous piece. One single piece does both the job, because providing a stiffener, again the question of end connections will come, right. And it may so happen, as we have drawn, the way that depending on the depth of the dowel bottom and the size of the brackets, there will be small space left. So, providing another small stiffener, it should have a continuity between the brackets connection. So, that may prove to be difficult alignment problem, because not all will be correctly spaced. The problem is, even if there is a 5 millimeter, it is out of alignment, that itself will be the thing will not fit, right. So, instead one single piece can be taken, which can have a sufficient play in this direction. If I put it little upwards or little downwards, it does not matter, because I have sufficient clearance in both the sides. These are my clearances, isn't it? There is a clearance. They are generally of the order of 50 millimeter. They are generally of the order of 50 millimeter. Why not 25? Why 50? Again, why not 100? The reason is, it is not 25 simply because then what happens, the space will become very narrow, that clear space, and becoming narrow means it becomes difficult to maintain that point. You will have to provide painting, otherwise there can be a possibility of corrosion, right. So, once the construction is done, each and every nook and corner has to be accessible for painting purpose. This painting is necessary, unless that is done, again it will lead to corrosion. So, that is why it cannot be small. Keeping that in view, we can keep 100 millimeter, then it will be more comfortable to paint. Then again what happens, your bearing area becomes less. Suppose your depth of this is 200, and if I keep 100 millimeter gap, then this becomes only 100. So, support area becomes less. So, it has to be some optimums. Generally 50 to 75 millimeter is kept. That is the simple logic. Okay. So, that is how this duct keel. So, here this entire thing taken, this entire construction is referred to as duct keel, because it forms a duct. Well, now, so that way we have looked into the what do you call, dowel bottom construction, right. Wing tanks. Well, wing tanks are not there in all ships, in the bulk area mainly, but all ships will have dowel bottom construction. The construction philosophy is same. Duct keel. Well, duct keel is also not a must, but it is preferable, it is a good design practice to provide for a duct keel. Well, if the vessel is, sufficient space is available, if the vessel is very small, say a river barge, right? River barge means whose carrying capacity is say 300 tons, 500 tons. So, they are probably providing a duct keel kind of arrangement, a double bottom, all these things may not be there at all, right. So, the question does not arise, but in any other ocean going vessel, whatever is the size, possibly it would be a good practice to provide for duct keel always. That may add marginally to the cost, but in the long run it will be beneficial for the ship owner, simply because possibly he will save much towards maintenance of his utility lines, because in ships there are various kinds of pipelines, right, freshwater line, seawater line, bilge line, firefighting line, so many pipelines will be there, cables, electrical cables will be running. So, maintenance of those becomes easier and better. So, duct keel. And then we have, as we see the vessel, these two parts. This is forward end construction, aft end construction, right, and rest part of the construction within this zone, they are generally identical. Only difference is in the engine room. The difference is like this: you have the holds, you have the double bottom. All construction what you have talked about, the double bottoms, these double bottoms will be identical. That means the same methodology will be taken. Inner bottom longitudinal, bottom shell longitudinal, floors, bracket floors, plate floors, solid watertight floor, all those things will be there, right. Similarly, in the side shells, the decks will be same, identical. By identical, I mean identical arrangement. The dimensions of the stiffeners, so called scantlings of the stiffeners, or the shell plating thicknesses, they may be different, but the arrangement, deployment of stiffening members, all these things will be same. In engine room also the decks, shells will be same, only difference will be in the double bottom. What is the difference? That here we have floors at every frame space, rather I would say plate floors at every frame space, whereas in other places the plate floors are at intervals. And in between you have so called bracket floors, that is the difference. Otherwise, again mostly everything remains the same. That is how the greens are the say bracket floors, that means we will have that bracket floor arrangement, only the two brackets supporting the bottom and inner bottom longitudinals and the center girder. If I have a what you call duct keel arrangement, then also the same thing. In case of a bracket floor arrangement, this part of the plating is not there, right. This part of these three lightning holes I have drawn, that means this part of the plating is not there, only this plate and this, these two together they will be taken as the bracket floor, right. That means this is basically a bracket. What it is doing? It is connecting the bilge plate with the inner bottom plating and the immediate stiffeners, longitudinals. So, a connection is being made. Similarly, here the inner bottom plating, the bottom shell plating and the one of the side girder, right. So, that is what it is, the bracket floor. And but in engine room the difference is all frame space will have this kind of plate floor arrangement. This is a plate floor arrangement. It is done because because there are very many concentrated loads are there. The main engine is there, the various auxiliary machineries are there, and so on, right. That is why putting a solid floor or putting a plate floor, you see solid floor also called as plate floor, that does not mean that it is a watertight floor, it's just the name like that. So, a plate floor is obviously a much stronger arrangement than a bracket floor, right. So, that is provided because to support many concentrated loading which may come in the engine room, that is number one. Number two is by providing additional rigidity, it changes the frequency of vibration of the structure, all right, and as such it brings down the natural frequency of vibration. So, here engine will be there, it is a moving machinery, right. So, it will generate or it will provide for an exciting force for vibration. What would be the frequency of that exciting force in the engine room? The engine room structure, it may get subjected to vibration, you know, like when you sit in a car, when you switch on the engine, you feel a vibration. That means, where from the vibration is coming? From the engine. Why it is coming? Something is rotating there, something is happening. What is happening? Something is rotating, that is getting transmitted. Now, obviously, if the vibration is too much, you won't like it from the comfort point of view, and secondly, it may lead to what? What it may lead to? A failure, a fatigue failure, a fatigue, because vibration means, what vibration is? What is the difference between vibration and oscillation?
Oscillation is particular small, vibration as a whole thing vibrate. So vibration is random.
No.
Oscillation is having some fixed frequency.
Oscillation is about to fixed points.
Vibration also I can say, if it is being excited by a sinusoidal force continuously, so about a fixed base it will go up and down. Imagine a situation, it is going up and down, it is vibrating. I say no, it is oscillating. Oscillating is a rigid body motion and vibration is a elastic deformation taking place. The body is elastically deforming. Oscillation would have been this. In oscillation, the rigid body motion is taking place. The bulb, always we tend to show like this. Why? Because when you talk about oscillation, think of pendulum, right? So, when a pendulum is moving, it is oscillating about the center line. There is no deformation taking place. When the ship is rolling, it is oscillating. The whole rigid body motion is taking place. It is not deforming. There is no deformation taking place. But thing is vibrating, then actually say this plate vibrating, it will make motion like this. So, it is actually what is happening? Elastic deformation. The deformations are within the elastic limit. Had it been plastic deformation, it would have remained like this, deformed and remained, right. So, deformation is taking place, but within the, it is following the Hooke's law, remaining below the yield point. So, it is sort of when the exciting force is removed, it comes back to its original shape. When the car vibrates, you switch off the engine, it becomes steady and there is no physical deformation noticed anywhere, right. So, there is a difference. So, vibration is a result of elastic deformation. That means, a elastic deformation is taking place. So, what is happening in the process? That means, the material is subjected to tensile stress, compressive stress, isn't it? When it is going like this, the top fibers are in tension. When it is going below, the top fibers in compression. So, being subjected to a cycle of loading or cyclic loading, that may lead to fatigue. Means you have seen, if you want to break something, you do like this and it breaks. Why? So, that is what may happen. That means, that may initiate a crack formation somewhere here and may lead to failure. And worst is that vibration amplitude, if it increases, resonance. So, to avoid resonance, to make it more rigid, more stiffened, such that its frequency, the fundamental frequency of vibration of the structure falls below the exciting frequency. Exciting frequency is nothing but the RPM of the engine and its multiples, right? RPM of the engine and primarily its multiples, the number of propeller blade on that. So, that is the difference here in the double bottom engine room. Rest other things are same. And then we will look into the forward end construction and the aft end construction. Little bit we have already talked about forward end construction. We will try to see it little more in detail. Okay.